Hi guys, in this video we'll take a look at solutions to trigonometric functions, solving trigonometric equations, examples, and then we'll finish with a summary.
So how can we solve trigonometric equations? So far we have learnt how to solve equations using algebra. In particular, if we have the equation 2x equals 4, then we can divide by 2 to get that x is equal to 4 divided by 2, which is 2. Or if we had a slightly harder equation, x squared plus 5x minus 3 equals 3, then we can subtract the 3 to the left hand side and factorise to get that x minus 1 multiplied by x plus 6 equals 0, and then we solve and get that x equals 1 or x equals minus 6. However, equations may also contain trigonometric functions. Consider the equation tan squared of x plus 4 sine of x equals 2. Or consider the equation cos of x equals 2 sin x cos of x. We have seen that the trigonometric functions are periodic, meaning they repeat over a certain period. In particular, if we'd like to sketch the graph of y is equal to sine of x, we have our maximum at 1 and our minimum at minus 1, and then we have representative values 90, 180, 270, 360, 450, 540, 630, and 720. The function is periodic with period 360. And therefore the sketch looks like this. And between any two subsequent points we have this 360-degree distance. And similarly for the graph y is equal to the cosine of x, it has precisely the same period, and therefore it is periodic with period 360 degrees. And so therefore the distance between any two subsequent points is 360 degrees. We take the same pattern and repeat it on and on. Lastly, we have a slightly different graph, y is equal to the tan of x. Now we've seen that this is periodic with period 180 degrees. And we've also seen that the values are 0 and then 90, 180, 270, and 360, and in the opposite direction, minus 90, minus 180, minus 270, and minus 360, and on in both directions. The distance between subsequent points in this case is 180 degrees. This means that for one value of a function there are many solutions, depending on the range of values being considered. Let's say we're asked to solve the equation cos of x equals 0.7 in the range 0 less than or equal to x less than or equal to 450. And again, these are in degrees. Then we take our graph of y equals cos of x, and we also plot on the line y is equal to 0.7, as we have an axis value here at 0.7, and we see there's some intersection points here, here, and here in the required range. And then we can write therefore, say, x1 here, x2 here, and x3 here, and these are going to be the different solutions to the equation. For equations involving trigonometric functions, there may be more than one solution, depending on the interval. In this case we have three solutions, x1, x2, and x3. Because this corresponds to the interval 0 degrees less than or equal to x less than or equal to 450 degrees. Other intervals may give different numbers of solutions. So how can we solve trigonometric equations in general? Many trigonometric equations may be generalized to one of three types of equations. Firstly, we have the type that a sine of theta equals b. Next, we have the type that sine of n theta plus a is equal to b. And then we also have the type that a sine squared theta plus b sine theta plus c is equal to 0. Each of these types of equations are solved differently. We solve this first type of equation by rearranging. We rearrange and obtain that the sine of theta is simply equal to b over a. We can then use the inverse sine function to solve for theta. This type of equation we use substitution. We use the substitution that capital X is equal to n theta plus a. This gives us the new equation sine of capital X is equal to b, and we can solve that equation by the same method as above. And similarly, this type of equation uses normal quadratics. We use the quadratic formula and get that the sine of theta is going to be equal to minus b plus or minus the square root of b squared minus 4ac over 2a. When performing a substitution to solve an equation for a given range, we need to alter the range when solving for the new variable. Let's say we had the equation sine of 2 theta plus 60 is equal to 1/2. And let's say we were given the range 0 degrees is less than or equal to theta, which is less than or equal to 360 degrees. Then we would use the substitution capital X is equal to 2 theta plus 60, the inside of the sine function. This gives us the equation sine of capital X is equal to 1/2 to be solved. But the question is, what is the range of X? We can do this by writing the original variable in terms of the new variable and substituting into the inequality describing the range. We have our new variable capital X is equal to 2 theta plus 60. We can rearrange this to get that theta is equal to 1/2 lots of x minus 60. The range we've been given is 0 degrees is less than or equal to theta, which is less than or equal to 360 degrees. By substituting in, we get that 0 degrees is less than or equal to the 1/2 lots of x minus 60, which is less than or equal to 360 degrees. And then we're looking to solve this for the inequality for x on its own. We start by doubling and we get 0 degrees is less than or equal to x minus 60, which is less than or equal to, by doubling, 720 degrees. And then we add 60 to both sides and we get 60 degrees is less than or equal to x, which is less than or equal to 780 degrees. And so our equation becomes to solve the sine of capital X equals 1/2 over the range 60 less than or equal to x less than or equal to 780 degrees. We then have to remember to use the rearranged substitution formula to convert the solutions for x into solutions for theta, the original variable. We again had that our capital X was defined by 2 lots of theta plus 60. We rearranged this and we got that theta was equal to 1/2 of x minus 60. Let's say our different solutions were x1, x2, x3, and so on. We get our corresponding theta solutions, say theta 1 to start with, by just doing 1/2 of the corresponding x1 minus 60. And you get the others by doing the exact same thing with x2, x3, and so on. We may come across trigonometric equations that contain more than one type of trigonometric function. For example, the equation tan squared of x plus 4 sine of x is equal to 2. Or similarly, 2 cos of x plus 3 sine of x equals 1. Lastly, tan of x plus 4 sine of x over cos of x equals 2. In this case, the equations can be manipulated using trigonometric identities. In particular, our favourite identities so far are sine squared of theta plus cosine squared of theta equals 1, as well as that tan of theta is equal to sine of theta divided by cosine of theta. We aim to obtain an equation involving only one trigonometric function. For example, we'd like to transform our equation so that we get equations like the following. Sine squared of x plus 2 sine of x plus 2 equals 0. This equation only involves the sine of x. Or similarly, the equation cos of 2x plus 3 equals 1/3. This equation only involves the trigonometric function cos of x. Or lastly, 2 tan of x plus 8 equals 0. This equation only involves the trigonometric function tan of x. This makes it easier to solve equations by sketching the graph of a function to obtain all of the solutions within a given range. Again, these are the sketches of the graphs of y is equal to sine of x over the range 0 degrees less than or equal to x less than or equal to 360 degrees. Similarly, we have y is equal to cosine of x over the same range. 0 degrees less than or equal to x less than or equal to 360 degrees. And similarly, we have y is equal to tan of x over precisely the same range. 0 degrees less than or equal to x less than or equal to 360 degrees. We can use these graphs to solve the equations once we've reduced the equations to only having one trigonometric equation. Let's take a look at some examples. Our first example asks us to solve the equation 7 sin x equals 5 for the range 0 degrees less than or equal to x less than or equal to 360 degrees. Our first step is to rearrange the equation to solve for a value of x. We can solve for one initial value of x that is the simplest value. We can rearrange our equation to get that the sine of x is equal to 5 divided by 7. And therefore we get that x is equal to sine inverse of 5 over 7. And this gives us x as equal to 45.6 to 3 significant figures. Our second step is to make a sketch of y equals sine of x and y equals 5 over 7. So we have our 90 degrees, 180 degrees, 270 degrees, and 360 degrees. These are the important values within our range 0 up to 360 for x. We have our graph y is equal to sine of x, but we also have this line which is y is equal to 5 over 7, since we're looking for the intersection between these two graphs. So therefore we have this intercept value here of 5 over 7. We have these two intersections we can see here and here for our range, but we have already found this value here since this is our acute angle value, 45.6 degrees. And so our third step is to obtain the other solution by symmetry. Our second solution occurs here. This is the solution we'd like to find. We have the symmetrical equation sine of x is equal to sine of 180 minus x. And therefore, since 5 over 7 is equal to the sine of 45.6, using our symmetry equation, this is equal to the sine of 180 minus 45.6. And this gives us the sine of 134.4. And therefore our last step is to write down the valid solutions. We have that the solutions are x is equal to 45.6 degrees and 134.4 degrees, and is both to one decimal place. Our second example asks us to solve the equation cos of 2 theta plus 50 equals minus 1 for the range 0 less than or equal to theta less than or equal to 360 degrees. Our first step is to introduce a new variable capital X to simplify the equation. Let us let x be the inside function, 2 lots of theta plus 50. Our equation therefore becomes cos of capital X is equal to minus 1. Our second step is to modify the range. Our range is 0 degrees less than or equal to theta less than or equal to 360 degrees. And so we can obtain the inequality for capital X by doubling the endpoints and adding 50. And so we have as our first endpoint 2 lots of 0 plus 50, and as our last endpoint we have 2 lots of 360 plus 50. And so we have 50 degrees less than or equal to capital X less than or equal to 770 degrees. Our third step is to provide a sketch of the graphs y equals cos of x and y equals minus 1. We have at first a sketch of y equals cos of x. And we can also sketch the line y is equal to minus 1 over the range and look for solutions. You may notice that our graph only goes up to 720 even though we needn't to go up to 770, but it's all the way up here at 720, and the next time it will reach the minimum will be at 720 plus 180, which is 900, and so there's not another solution in that missing range. And so we see that our solutions are here and here. Our fourth step is to deduce the point of intersection of the two graphs. We have that the solutions are x is equal to 180 and 540 by looking at the graph. Our fifth step is to use these to calculate the solutions within the range for theta. Recall that capital X is equal to 2 theta plus 50. By rearranging, we get that theta is equal to 1/2 lots of capital X minus 50. And we have our two solutions, x is equal to 180 degrees and x is equal to 540 degrees. And we can substitute in to get that theta is equal to 1/2 lots of the 180 minus 50. And therefore this is equal to 65 degrees. And similarly here we can get that theta is equal to 1/2 lots of 540 minus the 50. And therefore we get this is equal to 245 degrees. Our last step is to write down the solutions of theta for the given range. We have that the two solutions are theta is equal to 65 degrees or 245 degrees. In the range 0 degrees less than or equal to theta less than or equal to 360 degrees. Our last example asks us to solve the equation 4 sine squared of x plus cos of x equals 1 over the interval 0 less than or equal to x less than or equal to 360. Our first step is to recall the Pythagorean identity. We have that sine squared of x in general plus cos squared of x is always equal to 1. Our second step is to rearrange to write sine squared of x in terms of cos of x. We are hoping to get an equation only in terms of one trigonometric function. This will only be sine of x or cos of x as the one trigonometric function. Now it can't be cos of x because we have no equation to get cos of x in terms of sine of x. Not without introducing square roots, but we do have an equation, as we just found, for getting sine squared of x in terms of cos of x. And so we have that sine squared of x by rearranging is equal to 1 minus cos squared of x. Our third step is to rewrite the given equation in terms of only cos of x terms. Our equation is 4 lots of sine squared of x plus cos of x is equal to 1. And therefore by substituting we get 4 lots of the sine squared of x, which is 1 minus cos squared of x, and then plus cos of x, and then we have that equal to 1. We can expand out to get that 4 minus 4 lots of cos squared of x plus cos of x is equal to 1. Now this is an equation only in terms of cos of x. Our fourth step is to rewrite the equation in the form of a standard quadratic equation. We can multiply both sides by minus 1 to get our cos squared term having a positive coefficient, and so we get a minus 4, and then we have a plus 4 cos squared x, and then we have a minus cos x, and this is equal to minus 1. And then we can rearrange and we get that 4 lots of cos squared of x minus cos of x minus 3 is equal to 0. Our fifth step is to factorise the left-hand side expression. We could use the quadratic equation, but in this case we can factorise, and so we get the following. Our equation is 4 lots of cos squared of x minus cos of x minus 3 is equal to 0. And we can factorise this as 4 cos x plus 3 multiplied by cos x minus 1. And this is equal to 0. Our sixth step is to solve to obtain two solutions for x. We have to solve our two brackets equal to 0. We have that 4 lots of cos of x plus 3 is equal to 0. That's our first bracket. And our second bracket is such that cos of x minus 1 has to be equal to 0. We can rearrange to get that cos of x is equal to minus 3 over 4 for this equation, and that cos of x is equal to 1 for this equation. Now one thing to note is that sometimes we end up with quadratics that give us no solutions due to the fact that we get our cos of x being a value not between minus 1 and 1. Let's say we had one of our brackets being cos of x minus 4. That would be solved by cos of x is equal to 4, which clearly has no solutions, since cos of x only goes between minus 1 and 1. We invert these equations and we get that x is equal to 138.6. That's to 1 decimal place. And we have over here that x is equal to 0. Both of these are in degrees. Now these are only two of the solutions. There may be more in our range. And so our seventh step is to sketch the graphs of y equals cos of x, y equals 1, and y equals minus 3/4. These are the values of the right-hand sides of our two equations. So we have our graph of y is equal to the cosine of x, that's of course the wavy one. And then we have the graph of y is equal to 1, as well as the graph of y is equal to minus 3/4. And so we get a minus 3/4 on the axis over here. Looking at four solutions in the range 0 degrees less than or equal to x less than or equal to 360 degrees. And so we have our solutions here, 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 and here. Any other solutions, like for example here and here, are out of our range. Our eighth step is to calculate the other solutions by symmetry. We have that the cosine of x is equal to the cosine of 360 minus x. And so therefore we get that the cosine of 0, for example, is equal to the cosine of 360 minus 0, which of course is simply the cosine of 360. Similarly, for our other solution, we have a solution at 138.6, and so we have the cos of the 138.6 is going to be equal to the cos of 360 minus the 138.6. This gives us cos of 221.4. Our last step is to write down solutions for the given interval. We have our four solutions. X is equal to 0 degrees, 138.6 degrees, 221.4 degrees, and 360 degrees. Recall that the interval is 0 degrees less than or equal to x less than or equal to 360 degrees.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together, let's make A-level maths a walk in the park.